We propose NBNet, noise basis learning for image denoising with subspace projection. Image denoising is a fundamental and long-lasting task in image processing in computer vision. The main challenging is to recover a clean signal from the noisy observation. This problem is ill-posed as the clean IAMGA and noise are unknown. DNN-based methods such as DNCNN usually implicitly utilize image prior and noise distribution learned from a large set of paired training data. Although previous CNN-based methods have achieved tremendous success, it is still challenging to recover high-quality images in hard scenes such as weak textures or high-frequency details. Our key observation is that convolutional networks usually depend on local filter response to separate noise and signal. In this paper, we utilize non-local image information by projection. A set of image basis vectors are generated from the input image. Then we reconstruct the image inside the subspace spanned by these basis vectors. As natural images usually lie in a low-rank signal subspace, by properly learning and generating the basis vectors, the reconstructed image can keep most original information and suppress noise which is irrelevant to the generated basis set. Based on this idea, we propose NBNet. The whole architecture of NBNet achieves the state-of-the-art performance while only a smaller additional computational cost is added. The architecture of NBNet is based on a typical UNet architecture. NBNet has 4 encoder stages and 4 corresponding decoder stages. Skip connections pass large-scale low-level feature maps from each encoder stage to its corresponding decoder stage. The basic convolution building blocks in encoder, decoder and skip connections follow the same residual convolution structure. The proposed SSA modules are placed in each skip connection. As feature maps from low levels contain more detailed raw image information, we take the low-level feature maps as X1 and high-level features as X2 and feed them into an SSA module. The SSA module is used for projection. The projection contains 2 main steps. Basis generation. Generating subspace basis vectors from image feature maps. We denote X1, X2 as 2 feature maps from a single image. They are the intermediate activations of a CNN and can be in different layers but with the same size. Let f theta be a function parameterized by theta. So we can obtain the basis matrix V. We implement the function f theta with a small convolutional network. We first concatenate X1 and X2 along the channel axis as X, then feed it into a shallow residual convolutional block with k output channels. The second step is projection. Given the aforementioned matrix V whose columns are basis vectors of a k-dimensional signal subspace, we can project the image feature map X1 onto V by orthogonal linear projection with matrix P. The matrix P can be written as. Finally, the image feature map X1 can be reconstructed in the signal subspace by as Y, given by. Here shows our experiments. We conduct evaluations on benchmarks, including SIDD and DND. And NBNet achieves state-of-the-art performance on PSNR and SSIM with significantly less computational cost. Compared to MIRNet, we provide 39.75 PSNR compared to MIRNet's 39.72 by only taking 11.2% of its computational cost and 41.82% of its number of parameters. For the qualitative results, our method superior in the weak texture region like line pattern. These results demonstrated NBNet utilize the non-local information indeed. To gain insight about how the learned subspace projection works, we pick a sample image and inspect the subspace generated by the SSA module. It can be seen that when SSA is enabled, the dotted texture in the dark region is recovered in a way consistent with other part of the patch. Not surprisingly, this phenomenon finds its root in the projection basis vectors. As shown in the figure, many of the 16 channels contain the dots pattern that evenly span the whole image patch. We can thus reasonably surmise that this improvement should be attributed to the non-local correlation created by the SSA module. The weak textures on the upper part are supported by the similar occurrence in other parts of the image, and the projection reconstructs the texture by combining the basis with globally determined coefficients. To summarize, we analyze the image denoising problem from a new perspective of subspace projection. We propose NBNet, a UNet with SSA module for projection-based image denoising. We provide in-depth analysis of projection-based image denoising, demonstrating it is a promising direction to explore. Thank you.